In this segment, we're going to discuss how you can actually design a component that is under torsional loading. So as we know, torsion is a form of a moment on the material, but it is in a particular direction that causes shear stresses. So what I'll do is I'll review for you the idea behind torsion, how the stress is produced, the angle of twist that is associated with torsion, and we'll do that for round cross sections. And then we're going to just accept a few formulas for non-round cross sections and follow this with an application in an design example. So let's first look at the basic ideas behind torsion here. So if you consider torsion, we will be interested in finding the stress and the angle of twist in a round cross section. So if you have a round cross section like this and you have one end of the cross section that is fixed, and there is an axis upon which you have a torque T, for example, that is applied. So what happens is that in this case, if we have originally a fiber that is straight and is fixed at the point in the bottom, then after the application of the torque, this fiber will be moving to a new position, as you can see here. So if I have O, and then the point A will translate to another point that is called A prime, and the amount of translation is always along the perimeter of the cross section, as you can see here. So if the green amount of translation is a measure of the distortion of the material. So let's just make some symbols here. So if we connect to the origin of the circle, which represents the cross section O prime, for example, then the angle subtended here is called the twist angle theta. This is the twist angle, and the angle that is that can measure the shear is gamma, which is the shear angle. So the shear angle obviously is dictated by the length of the bar that we are interested in, and this is equal to approximately, in a small angle approximation, the radius of the cross-sectional area that is circular times theta. This is the green displacement that you see here, divided by L, which is the length of that bar. So if we now consider the stress, we have a shear stress. The shear stress is proportional to the shear strain, so we would have R times G times theta divided by L. In other words, we have some kind of a constant times R. In other words, the shear strain or the shear stress, both of them are linear with the distance from the center of the coordinates. So if we just consider another consideration here for the shear stress, then we can say that the applied torque should be equal to the integral of the forces, which is the shear stress times the area. This is the force that is generated in the element of area, and this we multiply by the distance away from the center. And if I take this distance in general, I can call it rho, which is kind of an indication of the distance away from the center. So if I have, for example, the distances here, if I measure from the cross section, so the distance is rho up to any point of interest at this point, and then the cross section itself has a maximum rho of r. That's the characterization of the cross section. So if we do an area integral, then we see that the torque is equal to tau, which is, now we can actually replace tau with k times rho, like from the previous equation. So it would be a constant times the integral of rho squared dA over the cross-sectional area. So that we see that kind of integration that we have here is an area integral, and this is called J, the polar moment of inertia, polar moment, or second moment of area, polar moment of area. So every cross section has a polar moment of area, and therefore the constant that gives us the proportionality between the stress and the distance from the center O is just simply the torque divided by J. So if we take that and see now that the stress will be T over J times R, and therefore we would just now, if we let's add another page here of the current template. So in this case, we conclude that tau is equal to T times rho over J, and this is the tau at any position rho. The maximum value of tau for the from torsion is when rho is equal to R, and we will get this value. And notice that I have here gamma is equal to tau over G, and gamma is related to theta as R theta over L. So I can conclude that the shear strain itself, gamma max, that corresponds to this, is tau over G, so it'd be T times R over GJ, and theta, which is the angle of twist. So if you go back to the angle of twist in here, the angle of twist is equal to gamma L over R. So we would have to take gamma L over R, and R will cancel, so it'll be T times L over GJ. So these are the basic conclusions that we have for torsion, and that is the shear stress is linear with the distance from the center of the cross section, and this maximum at the outside fibers. Shear strain is also linear, and it's maximum at the outside fibers, and is equal to the shear stress divided by G, which is the shear modulus, and that the angle of twist is now proportional to the torque. It's a TL over GJ. So GJ, the product of G times J, we call it the torsional rigidity, because it if the cross section has a very large value of GJ, then it will be very rigid and we cannot twist it very easily. So this is kind of the main ideas, and let's now just review that again here with a little bit clearer pictures, and then move on to non-circular cross sections. So if we look at this, we'll see that this is the main result, and you can see here that I have the theta, the angle theta is TL over GJ, as we indicated before, and that the torque is represented with a kind of a thick arrow along this axis here. Let me take this out, and then this is the angle of twist theta, and then if you have an element on the side before application of the torque, it looks like this at B, and then after the application of the torque, it will be sheared and twisted, and this is basically the shear stress that we have here. And therefore we can actually look at the shear stress as T rho over J, and its maximum is TR over J, as we discussed it before. Now, these assumptions are based on the fact that we have a cross-section that is circular. If we have a non-circular cross-section, for example, if we have a rectangular bar that is B times C, where B is the longest side, so in this case, the bar is going to be a cross-section that will look like this. So this is the longest side is B, and the shortest side is C. And then it has a center, and then we are applying a torque T. In this case, the shear stress is 0 at the corners, so we're going to take these without derivation, that the shear stress is 0 at the corners, and then the shear stress is going to be maximum in the middle of the longest side. And the value of the maximum shear stress is T divided by B squared times 3 plus 1.8 over B over C. And then the angle of twist is TL over G, and instead of J, we have beta B C cubed. And these are values of beta that are given in the table in Shigley's book. So now, before we move on, I wanted to discuss the idea of power and how we're going to deal with like a source of power that is going to allow us to apply a torque. So as we know, then if we have a motor and the motor is running, so it has the ability to deliver power is measured in horsepowers. We know that in SI units, that it is measured in watts, but in more practical units, conventional units that we use here in design, the power is measured in horsepower. So we wanted to just know what is the relationship between the power of the motor and the torque that is applied to a particular component. And that's what I'll discuss here. So as we know, if we have a force and the force is multiplied by the velocity, that gives me power. But this is for linear motion. So if I want to have rotational motion, then the force, if I multiply by a distance away from the center of rotation, and then divide the velocity by the same distance away from the center of rotation, then F times R, I can call it a torque T, and V over R, I can call it omega. So the basic formula that we have is that the power is T times omega, where omega is in radian per second, and the torque is in Newton meter, and the power is in watts. So this is all in the customary units. If we have now the practical units, this situation is going to look a little bit different, where we actually have the power is measured in horsepower, and then there's a factor that comes in, and at the end of the day, the horsepower is equal to T times N, where N is not in radian per second, but it is in RPM. So we have T is in pound-foot inch, and N is in RPM, and the kind of a proportionality factor, that conversion factor, is 63,025. So this is going to help us quite a bit in converting the applied torque with the RPM. Note that the horsepower is proportional to the product of the torque and the RPM. So if the RPM goes up, then the torque will go down, and vice versa, which is something that we're all familiar with in automotive applications. So let's take now an example of a crank that is as you can see here, is attached to a fixed wall. In reality, this fixed wall can be something that we want to turn, but it has a very large inertia. But for the purposes of this example, we consider it to be a fixed wall. And we have a force applied on one end, and the force is a distance 1.5 meters away, inches away from the center of the shaft BC. And in addition to that, there's a kind of a rigid attachment between the two elements, because we have a shaft AB in here and we have another beam, basically BC. And we wanted to, number one, we wanted to draw separate free body diagrams, one for BC and the other one are for AB. And then we will come back and compute the maxima of the torsional stresses and bending stresses, because BC will be under bending and torsion, and AB will be under bending and torsion. We will also have numbers. Item C here, we want to locate a stress element on top of the shaft at A, right here. And we want to calculate the stress components acting on this element. And item D is that for this particular element here, we want to determine the maximum normal and shear stresses at that element. So there's a lot of different objectives for this example. And let's start with the free body diagram. So free body diagram, in here I'm going to break it into two parts. The cantilever BC is represented here by a straight line, and we have to be careful with the coordinate system. So we put a coordinate system, as you can see here, the coordinate system, this is the X, this is the Y, and this is the Z. And for this particular coordinate system, we wanted to look at the forces and the torsion, the torques and the bending moments that are acting on that element BC. So if you look back here, the force F, we can transfer it to point C here, but when we transfer it, the equivalent system will have to be the force itself plus the moment that is caused by the force, which is F times the distance of the transfer. So in this case, we will look at this and find that the force F is transferred to C, but comes with it is a torque T sub C, and the torque sub C is negative. Minus 450 K is the unit vector in the Z direction, so it's going in the negative Z direction. At the end of the arm BC, which is the other end here, the arm has to be in equilibrium. So to have equilibrium, then we must have a vertical force F exactly equal to the vertical force F at C, and we also must have a torque T1 that is opposing T sub C, and this also for balance, because we had a moment here, then we have a moment M1 that is in the X direction. This moment M1 is to balance the force times the distance, which is the 4 inches here. So F times 4 inch, then you get a moment here that must resist it to balance and give you the free body diagram. So that's kind of what we have for the arm BC. Now for the shaft, at the connection point B, we have to reverse everything. So F is reversed, and M2 is, now it's a moment, we call it M, but is actually balancing the torque T. And M1 is reversed and now is called T2. So M1 is the same as T2, and T1 is the same as M2. And that basically takes care of this side B. If we go to the side A, we just take now this force system, including the moments, and balance it. So at side A, we will have a vertical force F, the same F, and the moment M2 is balanced by a moment MA, and the torque T2 is balanced with the torque TA, as we can see here. And that pretty much completes the analysis, and the values are shown in here. You can work it out easily by yourself. So now we go to the next idea, and the next idea is that we wanted to have the bending moment causes a bending stress in the arm. So we wanted to look at the bending moment, and it will have a maximum shear and maximum near the shaft at point B, which is right here, because if we have a bending moment like this is going down, then the moment will be the largest at point B. And the moment is equal to the force times the distance 4 inches here, which is 1200. So the moment is going to cause a stress, and the stress is M over I times C. So M over I over C is BH. We know that I is equal to BH cubed over 12. And then we just have, or actually C is half of H. So with that, it comes out to be BH squared, and then you get half of that, you get 6 in here. So with that, we find that the stress that is resulting from the applied force F, the stress is axial and is like tension on the top here, and its value is 18.4 kpsi. Now next we find the torque, the effect of the torque. There's going to be a twist, and as we discussed it before, there's a torsion, and the torsion is caused by this force here that is torquing. So it's torquing the arm BC, and when it's torquing the arm BC, then the maximum shear stress is on the long end, like here, and it's equal to T over BC squared, and this is the 3 plus 1.8 over BC, and that gives us 19.4 kpsi, and the stress occurs at the middle of the 1 1/4 section. So if we look at this, the maximum shear stress due to torsion is going to be right in the middle in here. So if I have an element here, this element is going to be twisted because of the torque that is rotated, and there's going to be a shear in this element, and the shear is going to cause the maximum shear is 19.4 kpsi. So now we go to element at A, which is the last part of the problem. And the element at A here, it has two stresses. So if we look at this element, we'll see that we have two types of stresses. We have a bending stress. So if the shaft is like this, then it will be bent downward, which means that I have an axial stress in here. And then it also, if the shaft is like that, then it will be torqued. So you have a shear stress. In other words, we have two types of stresses at that location. The bending stress, we will obtain it from the maximum moment, and then we have M times C over I, and obtain the value of the axial stress. And then the other part is going to be due to the torsion, and that because we have a round section now, so it'll be easier. And the amount of shear is going to be T times R over J. And that's what I have here. So sigma X is M over I over C. And the moment of inertia, or the second moment of area for a round cross section I is equal to pi times d cubed over 64, and C is equal to d over 2. So with these we introduce them here and find the axial stress. J for a round cross section is pi times d cubed over 32. Here's pi. Let me take that back, because we have this has to be d to the power 4, and both of them will be d to the power 4 over 32. And then we multiply by c, which is d over 2. Then you get pi d cubed here, and also on the in the torsion side you get pi d cubed. So we will get two types of stresses. One is the axial stress is very high, 47, and the other one is the torsional stress, which is minus 14.5 at that location A that we are interested in. Finally, at the same point, now we can, since we have a biaxial stress, we have a stress state. It's a plane stress condition. We have all the stresses are at the xz plane. Then we can find the principal stresses. And according to now our knowledge with the Mohr circle, we see that the maximum stress sigma 1 is, remember Mohr circle is sigma 1 and 2 are basically the circle, the center. C is the radius of this, where the center of the circle is, and R is the radius, so it's C plus or minus R, and C is the center of the circle, which is this average stress, sigma x plus sigma z over 2, and R is the radius of the circle, which is the square root of sigma x minus sigma z over 2 squared plus tau squared. And that gives me the maximum stress to be 51.2 KSI. If I want to pursue this further, then I can find the maximum shear, and the maximum shear is the radius of the circle, of the Mohr circle itself, because the radius of the Mohr circle is the square root of the difference between the two normal stresses over 2 plus the shear stress square. So that's from our prior knowledge, and therefore we get the maximum stress now, shear stress, to be 27 KSI. So this example, it gives us a very good idea about how to design for torsion, either for a cross-section that is rectangular, or a cross-section that is round, and it has, the cross-section can have a combination of a moment and a torque and even an axial